All right, guys, good morning. Let's get started with the video. All right, so projectile motion is what you will be tested on. So let me just highlight what's important from this chapter. Main observations are the ones that you have to focus on. So these are always conceptual test questions. Bullet drop and the bullet fire from the same height. So which one is going to land first? All right, let me just set up some real fast. All right, so need to be able to see the chat in case you guys have any questions. All right, so this is good. All right, so let's get back to the observation. So he's going to drop a bullet. She's going to fire a bullet, right? So same height. As soon as she pulls the trigger, this bullet is going to drop. So the question is, which bullet is going to land first? Common sense will dictate that this is going to land first. All right, so people will argue with you. If you just say that both of them will land at the same time, nope, you're not going to win that argument. No one is going to listen. No one is going to listen because it's people have a certain amount of tolerance. As long as things are within the frame of their common sense, people will go along with it. Most people will say this is the one which is going to land first, right? And the reason is because this is falling unimpeded, and this one is going to take a while. It's going to take a while. It's going to take like half a mile, depending upon the power of the rifle. All right, so this is going to travel quite a bit before landing. So people will argue that this is the one that's going to land first. All right, and physics will claim that both of them will land at the same time. So we'll just get back to that shortly. That was a lead-in observation. The main observation is this one. Right, so where would you aim in order to hit a monkey from a tree? Provided that as soon as you fire the cannonball, the monkey is going to release its grip. So would you aim above the monkey, hit the monkey, or down below the monkey? Once again, the common sense will say you should be aiming down below the monkey. So the question is how far down below, if that's the case. So it gets complicated as soon as you make that solution. All right, so according to physics, what should happen is both bullets should land at the same time. That's what physics says. The reason, according to physics, is because once the bullet is fired, once it's out of once it's projected out of the rifle or fired out of the rifle, what's going to happen is the gravity takes over at that point. So the motion starts to happen under the influence of gravity, which is known as free fall. In free fall, everything is going to fall at the same rate. All right, so regardless of the horizontal motion of the bullet, it's still going to fall under the influence of gravity, and it's going to fall at a constant rate. So which means that it's going to accelerate downward while reaching the ground at the same time as this one is. So both should reach the ground at the same time because all objects fall at the same rate under the influence of gravity. So the horizontal motion doesn't matter. It doesn't matter how fast the bullet is moving horizontally. Everything is still going to fall at the same rate. That's the reason why both bullets should reach the ground at the same time. So if there is a test question, that's how you answer it. All right, so which bullet lands first, both at the same time, because motion is under the influence of gravity and everything falls at the same rate under the influence of gravity. How fast the object moves horizontally has no effect on how fast it's going to be falling. That's what it means. All right, so the mathematical modeling, so it's two-dimensional motion. Projectile motion is one of the things that you're being tested on. The second one is going to be a rotational motion. All right, so it's a full projectile motion. Initial angle, initial speed. Initial speed is happening at this angle. That's what it means. The motion is going to have a range. It's going to have a height. This is the amount of time it takes for this object to travel forward. This is known as the flight time. So the amount of time it takes for it to travel forward is the same amount of time for it to go up and down. In essence. So the amount of time it takes there is going to be the same as the amount of time it takes here along the vertical direction. Initial velocity is going to have an x component. It's going to have a y component. Final velocity is going to have an x and the y components. Out of that, you can actually construct the total final velocity. That's what we will have to do. There's going to be an initial angle. There's going to be a final angle. Now, mathematically, I decided to break this into two halves. All right, so one of them is a simple sideways projectile motion. Those of you guys who are taking college physics, what I refer to as college physics is the algebra trig-based physics course. That's the common name for it. All right, so you'll be testing on this. Mathematically, this one is simple. Those of you guys who are taking the more advanced version, which is the calc-based version, you will be testing on the full projectile motion mathematically. So the calc-based is going to be mathematically much more involved. All right, so along the vertical direction, the y direction, the motion is the same as free fall. So we are limited to using the free fall formulas. And I'm going to turn this into sideways projectile motion. So once again, for algebra trig-based physics, that's what these are the formulas that you're going to be using. So there's not going to be an initial speed along the y direction. As a result, these formulas will be reduced to these three formulas that you're looking at. All right, so along the x direction, along the horizontal direction, acceleration is going to be constant, which means that the motion along the x direction is going to be predictable, except the acceleration is going to be zero. It's going to be zero and constant, so that's still predictable motion. So we get rid of the acceleration terms. It's going to give us three reduced formulas, except the last one is the same as the second one. So the last one is redundant, so we'll just get rid of the last one. So Sideways projectile motion can be described using these 5 formulas, so that those are the formulas that we will focus on. All right, so we got 3 formulas for free fall on the y direction. And the projectile motion is a perfect parabola, which means that the horizontal speed is going to be constant, which means that the acceleration on the x direction is going to be 0. So it makes the motion. So no acceleration on the x direction or 0 acceleration. So x component of this motion is predictable as well. So the entire projectile motion is one of
television camera
predictable motion. All right, so in terms of problems to focus on, there are 2 problems that I'm going to focus on.
are on hand
This is one of them.
and they captured a death-defying stunt. Daredevil Jean-Louis Arola is about to attempt a dangerous mid-air plunge into the frigid waters of the English Channel. The risky maneuver calls for him to drop from the plane as it speeds above the surface of the water. Jean-Louis carefully climbs out and secures himself to the belly of the fuselage. The aircraft approaches the drop zone. Then, he slams across the surface of the water. And now, he's not moving. Another look at the ill-fated stunt reveals that the plane was traveling much too fast by smashing into concrete. The rescue team quickly moves in and soon has Jean-Louis safely out of the water. Vision cameras are on hand to capture a death.
All right, so it's sideways projectile motion. Airplane is moving about 80 miles per hour. And then this guy jumps a distance of about 30 feet, I think. So he drops 30 feet from that airplane. All right, so a number of things to analyze here. Number 1, you got the projectile motion. Number 2, you got impact. All right, so we'll do the projectile motion and then we'll do an impact analysis at the end. All right, so we'll do everything. All right, so this is an example problem that you need to focus on, which means that when you're studying for the test, make sure that you know how to do this problem inside out using the format. Make sure that the format is part of your muscle memory. All right, so these problems require you to practice. So the airplane is moving at 80 miles per hour. I got the formulas on the side, so this is going to be a sideways projectile motion. So the airplane is moving at 80. This guy drops 30 feet. We'll assume that the motion is under the influence of gravity and gravity only, so which means that we are ignoring the effects of air friction. So let's figure out the final speed on the y direction, this final speed on the x direction. Figure out the angle of impact. Figure out the total final speed and then figure out the angle of impact. All right, that's it. All right, this pertains to projectile motion at this point. Sideways projectile motion. All right, so I listed everything using the proper symbols. The next thing is I'll make sure that I have the proper units, metric units. Before doing anything else, make sure that everything is converted. All right, so everything is converted to the proper metric units. The questions have question marks next to them. These are the steady units, and these are the units that I'm going to be working with at the end in order to understand what's going on. Okay, so everything is also going to get expressed in the units that I can relate to. So I'm interested in the final speeds on the x and y direction, so I can construct the total final speed and then figure out the angle of impact. And these are the 5 formulas available to solve this problem. All right, so final speed on the y direction is the one that I'm interested in. All right, so I'm focusing on the formulas that's got the final speed on the y direction, right? Got the final speed, it's got the final speed on the y direction. All right, now I have to make a decision. Do I use this or do I use that? For me to be able to use this one, I need to know the time, and the time is not given. All right, so the time is not given. So this is not a good formula to use. All right, so if that's the case, let's focus on the third one. So the third formula is the one that I'm going to use, obviously, because I know the distance one, which is the letter y. All right, so let's use this one. Isolate the unknown, and I'm done. All right, so one of the things that, and this is probably the 50th time I'm saying it, and maybe this is the first time some people are hearing it, but I keep saying it. These are formatting tests. Every single test is a formatting test. You're not following the format, I'm not grading it, in essence. All right, it's just, I would not give you a passing grade. Even if I'm looking at it, I would not give you a passing grade unless somehow you are clearly showing work. This is not multiple choice. This is like writing an essay. It's not a yes or no essay. You just have to explain stuff, and you have to explain it in the proper format, in essence. All right, you make sure that you have the proper structuring of the sentences. Whenever you're writing something, you make sure that things are properly spelled. You're using the right alphabet. It's the same in physics. It's the same as in physics. All right, and just like in every other discipline, I'm showing you my work clearly so that you could see that there's a format here. I'm communicating it so you can see how it is done. I don't just grab numbers and start for no reason and I'll multiply and divide and then, hey, we got the answer. That's not how it is done. All right, so you don't use numbers until you're done with your algebra, and you do your algebra symbolically. Don't do anything else, just symbolically. This is not high level math. This is literally the simplest algebra that you can apply. This is like the very basics that you can remember from high school. All right, the only thing we're doing is we're literally doing algebra symbolically. The rules are exactly the same. And trig, sines, cosines, and tangents. That's it. You don't need to have a PhD in algebra or trig. You need to be able to do 5, 6 things really good, and then you'll get better. All right, so notice that immediately the symbols are important because you will see the same symbols in the formulas. And so you can just refer back and forth. You can start your eyes here and there, check to see which symbols are matching. Okay, while you're making decisions. So everything is in front of you in this section, everything that you need. This is what's given. These are known as initial conditions. And then just grab the formula because this formula is only one unknown, which is on the left, so we're good. Now you can plug the numbers in at this point. All right, so one single formula that I was able to isolate. All right, so it gives you a number in terms of meters per second. You're thinking, okay, good, so I'm done. No, you're not done. You're analyzing real life. 13, 14 meters per second doesn't mean anything to anyone. Convert it to miles per hour. It's up approximately 30 miles per hour. Now you can start to visualize it better. Another thing that I'm going to be looking at is make sure that whatever you're setting it up, I need to see everything on some kind of a diagram or a graph in this case. It's 2-dimensional motion. One dimension is on the x direction. The other one is the y dimension. Notice that I'm identifying each and every single term on this graph. Okay, coordinate system more like it. It's not a graph. It's a coordinate system. All right, so this is the height that this person is going to fall. This is the initial speed. I notice that now everything has a meaning. Every single symbol, I'm attaching a meaning to it. And then I'm looking at the final speed. The final speed has components. It's got an x component, y component. Out of that, I'm able to construct the final speed. And then out of that, I'm going to be able to figure out the direction of that motion. So it's visual, visual, visual. The classical physics is visual. It's amazing that you can visualize stuff. In modern physics, we have no luxury. All right, so it's straightforward. It's clean. All right, so I just picked the formula. I isolated the unknown, plug my numbers in. I get a number in terms of metric units. And then now I'm getting an estimate out of it. All right, so it's roughly 30 miles per hour. So all of a sudden, I'm able to clearly see what's going on in my head. So vertically, this guy is going to hit the ground, hit the water at 30 miles per hour. And then what? Horizontal speed is not going to change. I don't even need to know the formula for that. Conceptually, I get it because ignoring air friction, there's no reason for this person to slow down. So the person horizontally is moving at 80 miles per hour. So the initial and final speeds will be the same in terms of metric units, which is the same as 80 miles per hour. All right, so now that I got the initial and the final speeds, now that I got the x and y components of the final speeds, I can construct the final speed at this point. All right, so construction of the final speed requires calculus. For those of you guys who are taking the advanced version of physics, or trig, for those of you guys who are taking algebra and trig, it's the same. All right, it's called vector calculus. And if I'm teaching advanced physics, I call it calculus. If I'm teaching algebra, trig-based physics, I'll call it trig. Basically, it's the same thing. I'll show you a trig. All right, so we'll be using calculus in the sense that these are vectors, which means that the horizontal component has a direction. It's got a size. Vertical component also has a direction and a size. All right, so which means that these are vectors. So if you need to figure out the final speed, the total speed in this case, the total speed is not 30 plus 80. That's not how it is done because the direction is going to matter. This is motion on the x direction. This is motion on the y direction. So what we will do is called vector addition for those of you guys who are taking calc-based physics, or it's known as right angle triangle if you're dealing with college physics. It's the same. All right, the titles just changed. We do the same math regardless. All right, so what I'm doing is I just construct. Okay, so this is visual. That's the reason why you have to just draw things out and show me your work. In essence, so here's the x component of this motion. It's a vector. It's got a size. It's got a direction. The thing about vectors, you can move them anywhere you want on this page. It doesn't matter. As long as you're not changing direction and size, you can move them anywhere you want. So what I'm going to do is I'm going to grab this vector, just pull it down, and I'm going to make myself a right angle triangle. All right, so here's your right angle triangle. So here's the angle, 90 degrees, right? That's called the right angle. All right, so this is the height, and this is the base of this triangle. The angle is going to go right here. All right, so, and hypotenuse is going to be the total speed that you're looking at. So this is the final speed, this is the total speed. So square the base, square the height, is going to equal to the square of the hypotenuse. This is known as the Pythagorean theorem. Okay, so that's it. So this is, for those of you guys who are taking advanced physics, we'll call this calculus, vector calculus. If you haven't taken it, it's not prerequisite. Calculus is prerequisite for this course, but I got news for you. A lot of the calculus that we use is from Calc 2 and Calc 3, not much from Calc 1 usually. All right, so this is a good way to learn calc at the same time. Those of you guys taking algebra trig-based physics, this is known as trig at this point. All right, so the base is going to be this. So square this in terms of the metric units, the number in terms of the metric units. This is the height, so it's going to be 13.58. Square that, sum them up, take the square root. That's going to give us the final speed right there. Boom. So that's our final speed, 86 miles per hour, give and take. In terms of the conversions, notice that I'm not interested in the exact numbers here. I'm just eyeballing this. This is 30, this is 80, this is 86. All right, that's it. The actual numbers in terms of the metric units tend to be precise. The other ones I usually use approximations. I'm just trying to come up with some kind of a vision in my head that I can follow. All right, that's it. That's as far as it goes regarding projectile motion. All right, now the impact analysis. All right, so impact is going to happen at this velocity. All right, the impact, forget the impact analysis, the angle of impact. All right, so it's either sine, cosine, or tangent of theta. It doesn't matter because you got all the numbers. Traditionally, we use usually tangent. You can use sine or cosine, whatever's available for you. All right, so tangent opposite over the adjacent. And then you take the inverse of tangent on both sides. So this is the formula that you come up with. And then now plug the numbers in. And then you'll get the answer in terms of degrees. Okay, so for the multiple choice section of the test, make sure that your calculators are set to degrees, not radians. Most calculators, they're defaulted to radians. Just remember that if you're not getting the right answer, there's a reason for it, if you don't have the right angle. All right, so the impact analysis, I'm checking to see, I'm looking at the worst case scenario. So this person is hitting the water at 86 miles per hour, so this translates to 86. Hitting water means water is going to give at high speeds, you will break bones. So you'll probably get, at least in the worst case scenario, you should be able to get about 1/10 of a second. There was a bounce. I'm going to ignore the bounce right there because it makes the math complicated. So I'll bring the person to a stop in 1/10 of a second. So just want to know what the acceleration was in the initial impact. All right, so I'm just analyzing the initial impact. There's an impact here. The person comes to a stop and then bounces back up. All right, so the motion itself involves variable acceleration. So it's an example of jerking motion. Anything that involves impact is going to be related to jerking motion. So the final speed, in this case, is going to be 0. Initial speed is the speed with which the projectile motion ended. That's 86 miles per hour in terms of meters per second. All right, so acceleration is going to be about 400 Gs. Move the decimal to the left. It's negative 40 Gs. Survivable for a fraction of a second? Absolutely, because we know you can survive up to 140 for a fraction of a second. Notice that not only am I answering the question, I'm also justifying it immediately. Okay, because you have to justify it, guys, because it's not my opinion or it's my belief that this is survivable. No, you're just checking it up against the known facts at this point. 40 Gs, survivable, yes, because you can survive up to 140 for a fraction of a second under extreme constraints. Anything over 25, expect broken bones. So I would expect broken bones here. All right, so I'm just stating facts is there. You generate the numbers and check them against reality. All right. Part of the reason physics is difficult is because of how it is done. It's a weird discipline. A lot of sciences are done this way, but physics is more so. I think it's a fact-based thinking. All right, so the formulas matter. The formulas are summary statements usually. The definitions matter. The definitions matter. You need to understand the definition. I'm not talking about knowing something. I'm talking about understanding something. Okay, to an extent that you can actually solve problems using it. A lot of the problem solving is not mechanical. It requires a great deal of insight into what's going on. You end up using math as a language, and the math needs to be part of your muscle memory in a sense that you need to be practiced enough to do these problems easily on the test. All right, so what I'm saying is this is what you practice. In essence, I just isolated a problem. I'm just gonna ask you a problem. It's gonna be similar to this one. All right, it's gonna be the problem is gonna be within the framework of what I just showed you.
Yeah,
all right, so the problem to focus on is this one, problem number 3. All right, so to call it your homework, call it whatever you want. Make sure that that solution that I came up with just apply to this problem.
to plan as they leapt off the bridge while tethered to the cable.
Stand up. One, two, three, go.
But as the team was about to reach the end of their first arc, the cable snapped. And 4 men and 1 woman plummeted 70 feet at 80 miles per hour, slamming into the water with terrifying force.
Okay, I'm on the outside, helmet cam. Kenny, myself, Lori, Sarge. She does the front flip. Here we come, going into full velocity right here. Probably reaches about 78 miles an hour, right about here, 78 miles an hour. You'll see the harness disconnect from the cable right there. Didn't see just disconnect, my arm goes out, and here we come to the water. Pow! Oh, like a ton of bricks. So look at this splash, like 40 feet. Pick your action, though.
And according to plan.
All right, so a couple of things. Projectile motion. For 5 people, I'm doing it. At this point, the cable snaps. And at the moment the cable snapped, these guys were moving sideways about 80 miles per hour. So the horizontal speed is 80, and they're falling 70 feet from that height all the way down. So the distance is 70 feet. All right, so this is projectile. All right, so I just redo this problem. Just do this problem, not redo it. This is your homework. All right, so horizontal speed is 80, and then they will fall 70 feet. Okay, so what do I need? I need to know a bunch of stuff that I need to know. So let's just take a look and add on. let's get out of here. All right, so problem number 3 is the one that you need to focus on. All right, so they're moving 80 miles per hour, so that's the initial speed, 80 miles per hour. Along the x direction, they will fall 70 feet. So that's the motion on the vertical direction. So that's the vertical direction. So that's the height. This is really the vertical motion. All right, so figure out the time it takes for them to reach the water down below, the impact speed on the x direction, the impact speed on the y direction, and you can just add on. You can figure out how far along the horizontal direction that they will land. You can figure out the total speed, total impact speed, and then you can also figure out the angle of impact. Okay, so just make sure that you know how to do all of them. All right, so those are the things that you can actually figure out. All right, so these guys are doing a pendulum move. You got your pendulum. All right, so boom, 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 boom. And then they get disconnected. A couple of things happening at this point. So they're moving horizontally. So they will have a horizontal speed. And you get to splash down. So the motion is 2-dimensional. You got the x and y dimensions. So we got 2-dimensional motion under the circumstances. All right, so they will fall this distance on the y direction. That's going to be 70 feet. They will move along the x direction, on the horizontal direction, all the way up to the splash, all the way up to the splash down. They will have a final speed on the x direction. They will have a final speed on the y direction. On top of that, they will also have, okay, I don't like that. They will have a resultant velocity or the final speed. And they will have an angle of impact. Okay, so all of them are valid test questions. Okay, based on what I just gave you from that problem. All right, so you should be able to figure out the amount of time it takes for them to actually move forward. That's the amount of time it's going to take for them to fall. So every single symbol that you see is everything that you should be able to figure out. You should be able to figure out t. You should be able to figure out x. All right, so what's given is, let me just tell you what's given. So g is given. It's going to be roughly about 10 meters per second squared. The initial speed on the x direction is given. So it's going to be about 80 miles per hour. Okay, so what else? Distance fallen is given. So it's going to be 70 feet. All right, so what's given is important. And out of that, I can ask for any of these. I can say, what is the time? How far along the x direction people will move before hitting water? All right, so the final speed on the x direction, the final speed on the y direction, the final speed itself, angle of impact. All right, and all these are the questions that I can ask. And make sure that you guys know how to do all of them. Impact analysis, I'm not going to worry about it right now. I'm more interested in the full projectile. I'm interested in the sideways projectile motion for this one. All right, so just focus on problem number, what was the problem number? Problem number 3. All right, so as you're studying, just do this problem. And obviously look at the example before this problem. All right, so this is for algebra and trig-based physics. All right, so for full projectile motion. Okay, so this one mathematically more complicated. All right, so those of you guys who are taking the calc-based physics, focus on this one. All right, the initial motion velocity is going to have an x and y components. All right, so let's focus on the conceptual stuff first. The vertical component is influenced by gravity, right? So notice that the vertical component, the y component of this motion, the arrow is getting smaller as the ball is going up. It's getting larger as the ball is coming down. All right, so 1 second later, the ball is going to be here. 2 seconds later, it's going to be here. 3, 4, 5, and 6 seconds. This is known as a 6-second arc. And if the vertical component of the initial speed is 30 meters per second, going up against gravity, it's going to lose a speed of 10 meters per second for the next second. So it's going to be moving at 20. Next second is going to be 10, and the next second is going to be 0. It's going to be 10 in the downward direction, 20 and 30. So which means that the acceleration on the vertical direction is going to be 10. So it's going to be the same as gravitational acceleration. Horizontal component of the motion is not going to change because ignoring the effects of air friction, there's absolutely no reason for this to speed up or slow down, right? So if the initial speed, horizontal speed is like 50 miles per hour, it's going to be 50, 50, 50, 50. So it's not going to change. So you end up getting this projectile motion. Now the angle is going to be important in terms of maximizing range. Just remember, 45 degrees is going to maximize the range. So In problems, usually, if it says maximum range, just know that the angle is 45 degrees. The angle may or may not be given to you. So there's an assumption that you understand the concept. All right, so speaking of the examples, let's focus on the conceptual stuff a little bit and move back and forth between concepts and math. If you knew that the monkey was going to release his grip at the moment you fired the cannonball, where would you aim? Is the question. The answer to that question is straightforward. Everything is going to fall at the same rate under the influence of gravity, which means that the monkey and the cannonball should fall at the same rate from this line of sight. All right, so provided that you have the proper range, and provided that you're aiming directly at the monkey, and also provided that the monkey releases his grip, at the moment you pull the trigger, you should be able to hit the monkey at the same time. If the cannonball goes faster, you'll hit the monkey sooner. If it's not moving as fast, you will hit the monkey later, but either way, you will hit the monkey. All right, so among things that we covered. People inside the airplane in air turbulence will get slammed against the ceiling in the worst case scenario. So the question is why? And all of a sudden it gets a little bit complicated because if you're looking at this motion from this point on, it's projectile motion, it's sideways projectile motion. In projectile motion, everything falls at the same rate. So which means that the airplane and the people inside should be falling at the same rate. It's exactly the same as what happens inside a falling elevator. You shouldn't be hitting the ceiling. You shouldn't be hitting the ceiling because you and the elevator are falling at the same rate. So if this were projectile motion, the people would be fine. They don't need to be wearing seatbelts. They would feel weightless, but they would be fine. They shouldn't be hitting the ceiling. So what's going on here? What's going on here is this motion is not projectile motion. It looks like it's projectile motion, but it's not. It's not projectile motion because the motion is not under the influence of gravity. All right, airplane is falling not because of its weight and not because of gravity. It's falling because it's being pushed out. It's being pushed out by the forces generated within the air turbulence. And it's being pushed out at a rate larger than the gravitational acceleration. As a result, the people inside, shielded from the effects of this turbulence, they're falling under the influence of gravity at a constant rate. And then the airplane is falling faster. As a result, what happens? The ceiling comes back and hits them in the head. So that's what happens.
Steady like a leaf.
Yeah, you look nervous.
Really nervous.
Yeah, really nervous. Okay, tell me what you're going to be doing.
Last time I got yeses from everyone except from you, and I told you I will do anything to impress you.
And hang on a minute, I'm not taking responsibility. I didn't ask you to do this.
Kind of did.
You did kind of do that.
No, I didn't. Okay, just tell me what's going to happen here.
Well, hopefully I make it from the cannon over the helicopter and land on the bullseye.
Okay, that blade's going to be rotating.
Blades will be spinning.
Has anyone ever done this before?
This has never been done before. 48 people in history have tried human cannonballing. Half of them have been successful.
And the other half?
Well, the other half died.
Oh my gosh.
Even the ones that did make it have had some major injuries.
What the hell's he thinking? He's lost his mind.
That's my daughter right there. She is watching.
Okay, I think we should just get on with it because I'm feeling anxious.
Good
All right.
luck,
Wow.
Rico.
Okay, thank you.
Rooting for you.
Are you all ready?
He is nuts.
Yeah. We have an ambulance waiting here just in case something doesn't go as planned.
Bella! Good luck, Bella! Oh, gosh, Bella.
That'll take off head in a second.
Simon, I feel a little sick. I don't like this. Oh, my gosh.
Now he's in.
Power cannon. Full power.
Oh, my God.
Power.
Army cannon.
Oh, my God, no.
Full safety.
Oh.
Firing. 5, 4, 3, 2, 1.
Oh, my God.
Let's see if he's okay though.
You okay?
Is he okay?
All right, so conceptual portion of the test involve things like that, except the questions usually come from the lectures directly. All right. So every time there's a main observation, just focus on it, check to see how it fits in with the lecture. The main observations that I've given you up to this point was bullet dropped and fired, shooting a monkey down from a tree, airplane and air turbulence. Those are all of them are valid test questions. What I'm looking for is, if you have a proper understanding of
Hi,
it,
Bello.
you should be able to realize by looking at it that there was absolutely no risk for this person. There was absolutely no risk. All right, so if there's an illusion of danger, And if it's properly executed, this thing is 100% safe. All right, so I'm watching it. The reason why I'm amused is people's reactions. This guy knows what he's doing. Why am I so certain that this thing is 100% safe?
How are you?
It's projectile motion, guys. Projectile motion. What does it mean? Is projectile motion predictable? 100%. How? How do we know that? It's not my opinion that it's predictable. It's not my belief that it's predictable. It's just the facts. And what I'm looking for, what are the facts regarding this? Projectile motion, the full projectile motion, is the acceleration constant? Yeah, it's constant along the x direction. It's constant along the y direction. Along the x direction is 0. That's predictable motion. Along the y direction is the same as the gravitational acceleration. That's predictable motion. So which means that this entire motion that you just saw is 100% predictable. All right, they know where he's supposed to be landing. Based upon that, they've done the computations. They set everything to a certain angle. And obviously the cannon is going to fire at a given speed. And 100% of the time, it was going to hit the target. And then something weird happens. The projectile motion is predictable. Is this the way this was designed to work out? The answer to that question is absolutely not. Once again, when you're looking at this, I want you to be able to just immediately just scan and check to see if this is the way it's supposed to work out. I can immediately tell you, no, absolutely not. Why not? Because if you're in projectile motion, there's going to be a landing involved at some point, and you want to be able to survive the landing. So the impact time matters. So which means that you always want to go for a soft landing. So which means that you need to hit something that's going to increase your impact time. This guy is hitting something which is not going to be increasing the impact time. It's going to reduce the impact time. This thing is pretty solid. And obviously you got a bunch of cars here. I wonder why. The reason why they got a bunch of cars there, because it's supposed to be landing on top of these cars. Why? Because the cars will give, they will crumple. All right. This is this crumple zone. It's right here. The impact zone is right here. There's an X here, and then this guy ends up falling significantly short. Why is it that things are going wrong, given the fact that this motion is 100% predictable? All right. All of a sudden, this is something that you have to start pondering. So this is what happens in real life. This guy is given its speed. And then ramp is set to a certain angle. The distance is measured. Obviously, the landing spot, they put an X there, and this guy is falling significantly short. Why is he falling short? If projectile motion is predictable. Okay, notice that I don't even have to give you math problems to make physics interesting or mind-boggling, more like it. Okay, everything turns into a mind twister in real life. You do a little bit of math, but a lot of the problem solving is conceptual. All right, so why is it that the projectile motion is not working out there? All right, so the thing about projectile motion, you know, it's free fall. And you know it's predictable motion, right? So everything is going to fall at the same rate. Regardless of how fast this may be moving, this and that will reach the ground at the same time because
It's needed to match the solenoid.
Everything's hot. Let's do it.
all right, so
It's impossible to tell
When 5 equals 2.
until Adam analyzes the high speed and crunches the numbers.
both of them land at the same time in real time. In slow motion, it looks like the one which is falling ends up landing first before the one which is fired, right? Time difference is 400th of a second. So does this mean that physics is wrong? No, which means that the experiment is not 100% perfect because you can never have a 100% perfect experiment. Welcome to life. Okay, so which means that there's always going to be a percent error. If there's a percent error, you have to justify the percent error. In this case, a couple of things that you can focus on. Time spent inside the barrel, because the bullet which is fired did not start falling immediately. And then the fact that the fired bullets usually spin, so that generates the well. All right, so in the absence of everything is still falling at the same rate on the vertical direction, so we got that. While things are moving horizontally at a constant speed.
One-handed super and secret, great style as his right hand comes behind his back. And here, a new trick for Flowers. Not necessarily new in the sport, but they're the kind of the Western civilization. The trick name is the stripper. We're getting a little crazy here, folks. And also the rock-solid look at this. Over 80 feet, he's traveling with no hands or feet on the bike.
All right, so everything's falling at the same rate along the vertical direction under the influence of gravity, meaning that notice that both of them are falling at the same rate, so this person is able to retain a relative position. Horizontally, both of them are moving at the same speed. As a result, the person will look and feel weightless relative to the motorcycle. So let's project downward, moving forward.
Charlotte, North Carolina. 175,000 racing fans are on hand to watch stuntman Brian Carson attempt a record-setting jump. To succeed, he has to hit this ramp at over 100 miles per hour and leap over 4 flatbed trucks, each packed with explosives that are rigged to erupt in a wall of fire. Then he must land precisely on the red X atop these shock-absorbing stunt cars. In all, the distance he must travel is 250 feet. Brian is ready. The camera mounted inside his car captures a dramatic angle just as he punches the gas on his final approach. But there's big trouble. Brian's jump is well short of the mark, leaving him trapped inside the mangled wreckage.
As soon as the car left the ramp, I knew I was in trouble. I knew it. I feel something was wrong. The car angled the wrong way. I knew the suspension broke somewhere.
Brian's car plunges through the gigantic wall of bursting flames. But instead of hitting a landing mark, he nosedives directly into an explosive charge.
I landed face first, engine first, right in this pyro mortar that was blasting off 100 pounds of explosives right in my face. That's like throwing a dart 100 feet into it and hitting a dime. You couldn't do it.
The force of the explosion and the crushing impact leave Brian fighting for his life. It takes emergency crews 40 minutes to pry him free.
I was pinned, my foot was pinned, part of the car caved in on me, my left arm was shattered, broken, I was in a fog. It was a bad scene.
All right, guys, my timing is a little bit off on this one. You need to get
Charlotte,
coffee.
North Carolina.
All right, so what's going on is it's predictable motion. So they put the X right there, and they've done the computations. And they set the ramp to a certain angle. I think whatever the angle that they decided to set it to was part of the computation, the initial conditions. I'm looking at it, it's about 30 degrees. It's not 45 degrees. This is 30 degrees. All right. And then based on the computations, this guy was given a speed. So he reaches that speed 100% of the time. He should hit that target 100% of the time. So is it possible that he didn't reach the proper speed? Well, it's possible. There's a 0 chance that that's what happens here, because you're given a speed. If you're under it, you're not going to jump. So just go around one more time. So he's got the right speed. Everything is fine. The motion is 100% predictable, except in this case, it's not working out. So why is it that it's not working out? He's falling short. There's a reason why he's falling short, because the car angles the wrong way. Immediately, the car angles the wrong way. The problem with the car angling the wrong way is now it's going to have a profile. The car is going to have a profile in the direction of motion, in the horizontal direction. So there's too much of a profile, which means that the air friction becomes a factor. The car will slow down. It's going to slow down quite a bit. All right, so that's the reason why at this point the motion is unpredictable, because horizontally the acceleration was supposed to be 0 and constant. It's not 0, and it's certainly not constant. And it's a huge factor. I mean, this guy is falling short by at least 20 yards or 30 yards. So that's a huge, huge distance all the way down there. All right. And so the next question is, why is the car angling the wrong way? He's got his own theory, which I'm going to ignore, because that's what the mind does. It gives you all these theories, and a lot of them are usually wrong. The reason why the car is angling the wrong way, some of you guys are thinking because the engine compartment is heavier, gas, the weight doesn't matter, it's free falling. It's because more than likely he was told not to fiddle with the brakes. You're not supposed to apply the brakes right when you're up in the air. And of course, most people wanting to look smart, you're not going to ask why. And then it's not going to make sense to you, obviously, because why not use the brakes? Because upon landing, he wants to have control over the car, because he doesn't want to just go to the side or something. So up in the air, he applies the brakes. And then what happens is the wheels are spinning. And then when you lock up the brakes, what happens is that spin motion gets transferred to the car. So the car starts to slowly rotate in that direction, starts to move in that direction. As a result, it obviously ends up hitting the ground with nose first, and then it just tumbles over a couple of times. All right. So this is how things are done. All right. So I look at a case, I just look at it, and then all of a sudden you scan through everything that you need. Projectile motion is 100% predictable. It's not. So I'll explain why. That could be a really good test question.
Paul Smith, an 18-year-old high school dropout, on the roof of a Florida condominium. 3 of his friends have already jumped into the pool below. Paul, unfortunately, misses.
Yeah, problem like that. Go, recording. All right, once again, the conceptual understanding of physics is fairly obvious here. A lot of the common sense stuff. Number one, horizontal speed is not going to change. All right, so this pool down below is probably about 10 yards away from the base of the building. The only thing you have to do is just run maybe about 4 or 5 miles per hour. You have to do your running here. When you jump, you will maintain that horizontal speed. All right, so it's common sense. This guy, whose name we already know, Paul, last name is Smith, high school dropout, too much information, but at the same time, it's relevant information. At least I could tell what he was doing when he was off at home. These are road runner cartoons physics. All right. He jumps, and then he looks down. He realizes that he doesn't have the proper horizontal speed, and he's thinking that, oh, if he keeps running, it's going to make a difference. And guess what? It doesn't really do that. It doesn't do any difference in reality. All right, so he falls forward. Now, the projectile motion is so predictable. And the reason why it's predictable is obviously because the acceleration surface along the x and y directions It's a uniformly accelerated motion. They decided to pull a stunt during a stuntman convention, live on TV.
Right now, it's definitely
involving projectile motion.
too gusty. We wouldn't be going for it. It's worse than it was 15 minutes ago.
We're going to wait as we get down to 45 miles an hour.
Still, Bob, don't amp down yet.
Stay on over there, over the miracle. What's it happened before? They all come together, but not amp down.
Don't amp down.
All right. I told Bob don't amp down if you get a miracle.
There's a right way to do it, and there's a wrong way to do it. You know? You can't hurry up in the last 2 seconds and haul ass and dive 200 feet on fire.
All right, exactly. That's exactly what he's going to do. He's going to dive 200 feet. And because the projectile motion is so predictable, they're going to try to make it interesting. They will make it interesting by setting him on fire first. All right, that's the reason why he's a little bit nervous right now.
We're playing at the last minute. It might happen.
And this is being done live on TV.
Go ahead.
Doing a stuntman convention.
Go with the glass. Make sure
Our ground air is up to date.
2 to 3 minutes away.
John has just given the okay to wet him. That means that fuel strips soaked in a cocktail are being applied to Bob's suit right now. There's no turning back.
How are we looking up there, Neil? You have one more strip to put on him. Okay, we're 100% down here, guys. We're 100%. We'll go. Here we go. Get the cameras up.
Remember, we're about to see 3 stunts in one. Bob is set on fire and has to wait 8 long seconds for those flames to build before he can finally leap out of that window and free fall 20 stories into this airbag.
Light him, Dave. Light him. Light him. Go. Sit. Go ahead.
Here he comes.
Okay, come on, look at it. Right side, right side. Take it out. Take it out. Take it out. Get in there, boys. Back off a little bit. Back off.
Seeing your incredible free fall in the blur of real time. Now we'll show it to you in what we call movie time. Once again, Bob's perilous leap from 20 stories as captured by 11 film cameras.
All right, so he made it look easy. But by no means this is easy. What he did is incredibly difficult. And also it's highly choreographed. Okay, the first thing he does, he's free to move relative to the center of mass. Okay, so that's one of the things that we will focus on later on. And he does it deliberately because this guy is highly experienced. The first thing he does, he gets his body head down. Right? All right, the reason why he does that is because he's on fire. He's trying to protect his eyes. He's trying to protect his eyes from the flames. And he wants to see where he's going. All right, now this is not the best position to land on. You don't want to be landing on your head, obviously. And at some point, he's going to turn around. He's going to get his body power. Why do that? He's hitting an airbag, obviously. And as far as you're concerned, it shouldn't matter. It can matter, guys. Notice that he does not do a superhero landing on his knee and break his back. So that's where stuff is dangerous. So he's going to get his body parallel to the ground. And impact, this is literally about a second long. It's probably even less than a second. So the impact is actually, there's a sizable impact, but it's surviving. Just a second. I'll put the fire on. All right, so this is predictable motion. Projectile motion is kind of.
Now he's practicing the flip. That's how he'll have to land. He'll have to land on his back.
All right, for those of you guys who've seen this, Luke Aikens, this guy jumped out of an airplane without a parachute.
At 18,000 feet, the oxygen mask will come off. That will be from his cousin, Andy Farrington, who will be closest to him.
Is there a falling noise that they're moving horizontally?
There goes the oxygen mask. Now at 12,000 feet, he'll hear a beep in his helmet. That will tell him he's halfway home.
All right, now this is not 100% projectile motion because these people, air friction matters in this case. So he's able to position his body, he can adjust his speed, this and that. But the basic principle is it's still fairly predictable motion.
Momentarily, we'll see his
I don't think he can change his horizontal motion. The horizontal speed is going to be constant more or less.
jump team pull their chutes, and that means Luke is all alone for the rest of the way. At 6,000 feet, he'll get another beep in his helmet. There goes the chutes. Luke is on his own. crowd on the ground looking up. They have a visual on him right now. He's in. And he's kicking and moving. From here and look.
All right, so.
Hi, Bello. How are you?
All right, so compared to those two, this is nothing, right?
Steady like a
This is nothing.
leaf.
Yeah, you look.
All right, this thing is very
You
predictable.
look nervous.
Beautifully executed. It's
Really nervous.
Yeah, really nervous.
100% predictable. This is more of a show. And he pulled it out. Came up with a made-up story about 50% of the people not surviving this. It's completely made up, obviously, but he sold it. This is the sort of stuff that you can expect to have on the test. This is going to be involved. So it's a long jump. Draw things out, just put them on a coordinate system. Initial velocity is what we're looking for in terms of meters per second, miles per hour. The angle, the initial angle is given, so it's going to be 28 degrees. Range of motion is 7.8 meters. So that's a 7.8 meter long jump. All right, so I got the uniform motion formulas, excuse me, along the x direction as well as along the y direction. So acceleration is going to be 0. The last formula is redundant, so I get rid of those. Free fall formulas are on the right, so those are the ones that I would get to use. All right, so what else do we have? That's it. So initial speed on the x direction, the initial speed on the y direction. All right, so let me just back off a little bit. All right, so that's it. I got the formulas, I got what's given. So I need to know what the initial speed is. How do you do it? Okay, so this is the sort of stuff that requires practice, practice, practice. Okay, the problems that I'm doing usually are standard problems in physics, despite the fact that obviously I got my own spin on it, which means that you normally will get stuff from real life, and you will get stuff in terms of the British unit systems. Okay, just I want to tie everything to the way you experience life in essence. But the way these problems are solved is standard. Okay, every single book is going to have these standard problems, and this is a standard physics problem. So how do you solve a physics problem like that? Okay, it's trial and error for the most part until you figure out things out, and then you develop your own style. All right, I've been doing this stuff for 20 plus years, so obviously I got my own style, and my style is I always go after what I need immediately. All right, so I'm interested in the initial velocity, and there's not much given, but I know I can come up with the initial velocity by constructing the initial velocity from the components of this motion. So this motion is going to have an x component and a y component, and so I can get the x component from here. X component of the initial velocity is here. The y component of the initial velocity is going to be here and there. And I also got the angle. All right, so I got the x and the y components. X and the y components will be related to this initial velocity. How? All right, so the x component is going to be the sine of the angle of the initial velocity. The y component is going to be cosine of the angle of the initial velocity. So I got my expressions there. So I got some extra formulas. So the initial velocity x component is going to be located here. So let's start up with that formula. So that one formula which is going to be available. For the y component of the motion, I could either use this one or that one. And notice that the time is not given. So, but the amount of time it takes for it to move horizontally is going to be the same time it takes for it to go up and down. Okay, at least I got that information out of this one. All right, so my starting point is just let's get the x component, and then let's get the y component somehow. X component, I can get it from there. The y component, I can either get it from here or there, or I can get it from here. I can get it from here, or I can get it from there. Except 4 and 5 is useless because I don't know what the final velocity is on the y direction. So, which means that this is the only one that I'm going to be able to use by just looking at the symbols. All right, so here's the x component of the initial velocity expressed in terms of the initial angle. All right, so and notice that as soon as I express it, now I got the initial velocity, which happens to be that I'm looking for. All right, so now I got two unknowns. I know the distance, I don't know the initial velocity, I don't know the time, but I can figure out the time. So how do you figure out the time? Remember, guys, the amount of time it takes for it to go up and down is the same amount of time it's going to take for it to travel horizontally. Okay, so that's what I know. So this formula's got time in it. All right, so t seconds later, this thing is going to be on the ground. So the final height is going to be 0. All right. So in order to figure out the time, I'm going to end up using this formula. All right, so t seconds later, the height is going to be 0, because at that point, that thing is going to end up landing right there. All right, if that this is cosine, not sine. In my head, it was supposed to be cosine. Anyway, so final height is going to be 0, t seconds later. All right, so do we use plus or minus? Okay, the way you make a decision based upon that, look at the direction of the initial velocity. If it's going up against gravity, if it's moving in the opposite direction of the gravitational pull, use a negative. If it's moving in the same, if it's pointing in the same direction as the gravitational pull, just use a positive. All right, so the component, the vertical component is pointing in the opposite direction. Vertical component of the initial speed is pointing in the opposite direction, so I'm going to use a negative for that one. All right, so as a result, this formula is going to look like that. T is something that you can isolate from here very easily, so I'm just going to isolate T. And then instead of using numbers, which I'm not going to let you, because you guys are taking a more advanced version of physics, so your math is going to be a lot of back substitutions. I'm going to do a back substitution right there. All right, so this gets substituted in there. So what do we have? We will have 2 times. All right, so we will have this times T. T is going to be 2 times that. Everything in the blue. All right, now let's come up with an expression for the velocity along the y direction. It needs to be expressed in terms of the angle. So when we express it in terms of the angle, that one is going to be sine of the angle of the initial velocity divided by, what is it, g? All right, now take a look at that. So you have VO, so this one is going to be VO squared. You have the cosine of the angle and you have the sine of the angle multiplied by 2. So I simplify that, there's a square here. Okay, I messed it, but I think I'll go back and correct it. Okay, this stuff that I need to take care of here, there's a simplification that happens. So you got 2 times the sine of the angle times the cosine of the angle. This is going to be, this is known as a double angle formula. So you just have to use that to simplify it further. So that expression gets simplified to that expression. All right, so from here, I don't think we need the angle. All right, so you need to figure out the initial velocity from here, but that thing is squared all of a sudden. All right, things got mixed up a little bit. No, that's not correct. Okay. Oh, okay, so I made the correction later. Okay, because this is happening during the lecture. Evidently, I missed it when I was looking at the numbers. I said this doesn't make sense. The reason why it doesn't make sense is 83 meters per second. And that's the reason why you need to focus on the numbers. 83 meters per second would be over, God knows, it's almost 200 miles per hour. There's no way this guy was running at 200 miles per hour. All right. And this is how you kind of check your work at the end unintentionally. So this is happening during a lecture. I noticed that I'm missing a square. So I go back, make a correction. And then now you have to take the square root of this. And then you have to plug the numbers in. So it's 9.1 meters per second. This guy's running fairly fast. It's like over 20 miles per hour, I think. All right. So that's the sprinter speed. Okay. Over 20 miles per hour. That's the sprinter speed. All right. So that's how it is done. Okay. Redo this problem. Or find problems similar to this one and make sure that you know how to do it without using numbers. Okay. Notice that I use numbers only at the end. Everything else I need to see. Okay. This I can follow literally. If you're doing that, I go, okay, so I can see the assumptions here. All right. I'm going after something and then keep everything in the algebraic form. Okay, don't get into the numbers because if you get into the numbers, I cannot follow it. I will not follow it. I wouldn't even waste time. At your school, I have over 100 students, 120 or something, and I barely have 15 to 20 seconds to grade these tests. And obviously, I'm a full-time somewhere else. I have quite a few students there, and also I work on research. All right, so everything is formatted. You got 15 to 20 seconds to grade per paper. Literally just going through something like this would take me 10 seconds. All right, I can see the assumptions, I can see how they work, I can see the substitutions. Notice that when there was a mistake there, I was able to pick it out just fine. And then I go, oh, okay, so, and then I came up with the wrong answer. And then obviously you go, oh, something is wrong somewhere, but that's what happened during the lecture because the numbers didn't make sense. But the work was good, the assumptions were good. There was a simple error. So if you make a simple error like that, not a big deal. If the assumptions are good, I go, oh, okay, so it's carelessness, all right? Being careless happens to me, happens to you, whatever. I tend to be much more forgiving with that sort of stuff. The answer would be wrong. And then if you could just acknowledge that you made a mistake somewhere at the end, but you can figure out why, that's even perfect. So that I know that you're aware that you made a mistake somewhere. But the assumptions are good. If the assumptions are good, the formatting is good. With that, even with that mistake, I would have given you 95% of the credit. All right, because it's a simple careless error. In real life, if you came up with something like this wrong, you would know at some point to correct it. Okay, because also I'm forcing you guys to kind of convert things to the British unit system. So that if you come up with a number which is just outlandishly weird, you know something is wrong. All right, and immediately you can just take some preventive measures. You can go back, check your work, or blah blah blah. Obviously, it's a test. There's a time limit, but be reasonable. Okay, I'm much more forgiving if you do show work, explain stuff, and then when you make an error, mistake, or whatever, say, hey, I goofed up. And possibly even if you don't have time, you could say, oh, the mistake is there. I just didn't have time for it. Okay, fine. You know that you goofed it up. I know you goofed it up. That's fine. It's not a big deal. Okay, you would have a point deduction, but you wouldn't fail a test if it's explained in the way it is explained here. All right, just let's have an understanding of it. All right, so mathematically, those of you guys are taking university physics or the essentials of physics. Yeah, let's just go here. All right, so a bunch of problems. Not every single problem is related to the college physics. Not every single problem is related to university physics. The easier problems tend to be for college physics students. Okay, so the stuff to do is, this is problem number 6. Okay, so we'll look at problem number 6. So practice this one. Okay, so while you're practicing that one, that's the one that your test problem is going to be similar to this. Just go back and redo it your way, not my way. It's spent at least a few hours trying to figure that out. Find problems related to full projectile motion. Every book is going to have standard problems. I don't care which book you like. All right, take a look at the example problems and check to see if you can get to the right answer. All right, do 1, 2, 3 of them until you're comfortable. Make sure that you can do everything within a span of 20 minutes or so. You should be able to get it down to 20 minutes while showing work. And we're about the numbers necessarily. Make sure that you can do these back substitutions and play with it. Just play with it. This requires a little bit of practice. Okay, so we're done with that. Okay, so let's back out of this. All right, so the conceptual sections of the previous test, I put up a lecture video on that one. I put up a review, the answer video on that one. That's what I meant to say. All right, the math portion was not covered in that video. Okay, there was a math problem there. It's from a different school. So for you guys, the math problems were slightly different. So let's just go over those 2 math problems. Okay, so those of you guys who are taking college physics, algebra, trig physics, you had a math problem, which is slightly more involved than what was in the lecture, but it's still within reach. I was hoping that you would be able to do it. The part of the testing is I'm testing to see how well you can generalize what you understand so that you can do a similar problem to what's covered during the lecture. And part of it is I'm trying to gauge to see what level the school is at. All right, so this is a university. I usually teach at community colleges. The universities, the education level tends to be, expectation level tends to be higher. And so I'm just trying to check to see how I need to adjust the quality of these questions. I don't want to make them so hard that you're getting really discouraged. I don't want to make it so easy that you're not putting in an effort. So I'm looking at the feedback, and then I'm thinking, okay, so I think some of these test questions need to be adjusted, not the conceptual ones, but the math ones. The other thing that I'm learning is, from what I understand, none of the people who are taking university physics, which is the calc-based physics course, these courses are designed for engineering and physics students. So most of you guys are majoring in things related to biology or whatever, and for whatever reason, you're required to take physics at this level, which I appreciate. So which means that I'm going to go easy on the derivations, basically. So, and then I'm going to make it more applied to math. I'm probably going to ease up on it a little bit more, okay? Because there's no reason to make it so mathematical that we're missing out on the concepts, okay? Because the original purpose of the course is to prep you for engineering as well as physics. So, which means that I have to make some modifications. So I need that sort of feedback. So when you guys are struggling, not a big deal. It's just way too early to panic. You'll get better at it, okay? Students do get A's, they get B's, they get C's. A lot of people end up getting B's at the end because you kind of, it's like a video game. You will kind of struggle at first and you will get better at it. And that's where you guys are at, okay? It's perfectly fine. It's a way of thinking, which you're not used to. So you're just developing your skills. If you're feeling discouraged, just ignore the feelings. Just ignore the feelings, just keep at it, okay? A couple of things, either you don't know how to study or you're not putting in enough time. So start putting in the time. In terms of studying, focus on the concepts. Focus on the concepts that we cover during the lectures. Focus on the concepts that we cover during these recitation sessions. Okay, every single question has an answer that you should be able to find within the lecture notes. Okay, every single question. Okay, I don't pull questions out of somewhere else usually. The math problems usually an extension of the sort of stuff that we do. Okay, the multiple choice math portion of the test was a little bit goofy. Okay, because I had to post stuff from the test bank. I'm not used to using Blackboard. Obviously, I'm getting better at it. Okay, a lot of the times, if something is delayed, it's delayed because I'm trying to figure out how to do it the right way. And when I pulled in the test bank from one of the textbooks, I usually need the problems, multiple choice problems. And then you randomize everything. And as I was randomizing everything, I blacked out certain sections. Okay, I must have done something wrong. And all of a sudden, there were some high quality problems they were not intended, but most of you guys did well. So I'm just going to keep them as they are. And for those of you guys who need to do an upgrade, I'll let you guys do an upgrade on that. Okay, so at the very end, the questions were fair, but some of the questions were not the sort of questions that I intended. Okay, and you will still be able to do those questions, and most of you guys have. All right, so in the future, though, everything is going to be multiple choice. And then now that I know how to block everything correctly, you will get the sort of problems which are related to what we covered during the lectures. All right, so just be aware of that. So it wasn't intentional. The formatting of the multiple choice of the math section of the test was like, I was very surprised that there were questions there that were not intended. Like some of the questions required that you have to do calculations and come up with numbers and all that stuff and put down the typing numbers in. And, you know, that wasn't the intended purpose of it. So that made it much longer. All right, so this is the problem. So we got a chopper descending at the speed that's 20 miles per hour, right? And from this height, which is 800 feet above the ground, the package is dropped. So how much time does it take for the package to reach the ground? So which means that you will have to ignore the air friction. And then there's a bit of a hint. So the package's initial speed is the same as a helicopter's initial speed. So it's going to be 20 miles per hour. So it's going to be 800 feet. 20 miles per hour and 800 feet. All right. So, okay, guys, I don't have a calculator with me. So as I'm doing it, just pull out your calculators. I will need the answers from you guys. All right. So let's go to the worksheet. All right. So let me just draw this out. Okay. So here's the package. This package is actually moving with that initial speed. All right. So it's got an initial speed on the y direction. And the initial speed of this package is, what is it, 20 miles per hour? All right. It's 20 miles per hour. All right. And then obviously the package is going to land at some point. And it's going to be following this distance. So this is going to be 800 feet. So we got 800 feet. And then what's going to happen is it's going to take a certain amount of time for it to follow this distance. And that's what I'm interested in, question mark, in terms of seconds. How long does it take for it to follow? Okay, so one of the things that you notice is ignoring air friction, the only force acting is going to be gravity. So I'm just going to use an approximation of 10 meters per second squared for that. All right, so that's it. That's what we got. All right, so you got 20 miles per hour. Who's got the answer in terms of meters per second? All right, so I need the answer in terms of meters per second so we can proceed. All right, so you got 20 miles per hour. So take that number and divide by 2.24 and give me the answer. All right, guys, it's that silent. All right, so you guys don't have the numbers. If that's the case, I'm gonna proceed because I don't have time for the numbers usually. I usually look up to students for that sort of stuff. All right, so this is in terms of meters per second, and then this is converted to meters, right? All right, so let's make the assumption that you did the conversion. Step number 2. All right, so this step number 2 is algebra. Now we have to make a decision as to which formula to use. All right. All right, so it's free fall. So let's just grab the free fall formulas. Okay, so these are the formulas which are available for that use. Okay, so let's focus on the formulas. Which ones can we use for that purpose? All right, you do have initial speed. So this is not 0, so you have to keep them as they are. So the best thing to do is let's check to see what's given. All right, so we know the height in this case. All right, so we know what this height is. All right, so this is given. Time is what we're looking for. All right, so this formula, let's focus on this one. You cannot use this one because you don't know the final speed at the end. So this is not given. So this is not given, so you cannot use it. Likewise, you cannot use this one for the same reason. And all of a sudden you realize that this is the only one you can use because you look at the symbols and you got symbols for everything here. So the symbols here, the symbols here will match the symbols here. And that's it. Okay, so by looking at the symbols, that's the formula that I'm going to pick. All right, so now that I picked that formula, it's going to go into the algebra section. So this is initial velocity times time. All right, so it's dropping in the downward direction. So this is the formula that I'm going to use. And then you need to isolate t under the circumstances. All right, so how do you do a problem like this? Okay, so there are 2 ways of solving this problem. Number 1 is the quadratic formula, and number 2 is a substitution method. Okay, so either way, this is going to be involved. All right, so there's 2 solutions for this one. So solution number 1, use the quadratic formula. All right, so the first thing I'm going to do is I'm going to make this look like the quadratic equation. And then the quadratic equation looks like this. All right, so I need to make it look like the quadratic equation because this t and this t are the same, except this is taken to the 2nd power. So which means that this is a quadratic equation. And then stuff that you remember from the quadratic equations, they will look like this. There's a quadratic equation. And if you have a quadratic equation like that, if x is what you're trying to figure out, so it's going to be negative b plus or minus b squared minus 4 times ac take the square root, and everything is going to be divided by 2a. Okay, that's it. So this is what you need to import. Now, for you to be able to use a quadratic equation like this, what you need to do is you need to make this look like this equation. So which means that you have to move this term here and then have 0 on this side. That's the way it's going to be. All right, so what I'm going to do is I'm going to make this equation look like this equation first. So I'm going to rewrite things. Okay, now the equations look the same. And I'm going to change this portion a little bit to smooth this out. Okay, I'm going to make this positive, and negative is going to belong to the letter y. Okay, cool. And out of this, A is this term, B is this term, and C that you're looking at is going to be this term. All right, so I got my A. So A becomes, all right, now, okay. I got it right, but the order of the terms are wrong. Okay, the ID is wrong, right, but the order of terms wrong. All right, so let me just move things around so that these two equations, this equation looks like this equation. I need to make them look the same first before I apply. All right, so, and then I'm going to grab the coefficients. Okay, so let's move this, put a negative sign right there. Okay, now we got it. Okay. All right, so this is A, this is B, and this is C. Okay, now we got it. All right, so instead of using numerical, I'm just going to keep working with my algebra. All right, so A is going to be 1/2 g. B is going to be the initial velocity. And then C is going to be that. All right, so everything is going to go into this formula. All right, so this X now is going to become T. All right, so you get your B, which is this. And then we got plus and minus, open parentheses. We got B squared. All right, so which is going to be BO y squared minus 4. All right, so you got your A. A is going to be 1/2 g. Times C. So the C is going to be this term. All right, so C is going to be the negative y. And everything is going to be divided by 2a. All right, so A is this one more time. All right, and then you simplify it. All right, so you got your initial velocity, square this plus and minus. Once again, you got your initial velocity squared. All right, I messed something up. Okay, there's no square there. All right, so you got 2 here, you got 4, and you got negative times negative, so that's going to be positive. So we got our positive, so it's going to be 2 times g times the height. Take the square root of this section. And then we have 2, 2. All right, so these are going to cancel. So in the denominator, you have g. All right, so this is as far as it's going to go. That's one way of solving this problem. Okay. Mathematically, this is as far as it goes. Okay, what I wanted to see was everything in terms of the symbols. Some of you guys actually solved this problem, except you've done it numerically. I don't want you to do it numerically. I don't want you to go to the numbers. I want you to struggle. Let me see the struggle. All right, so it's 80% of the credit was coming from here normally. So the formatting has to be here. Some of you guys actually didn't even bother with listing anything. And then some of you guys just started pulling in the equations. Some of you guys decided that initial velocity was 0, which is not. This is a complicated problem. And some of you guys didn't do the conversions. Okay, so formatting is important. And some of you guys just did it numerically. And if you did it numerically and then came up with the right answer, which is fine, I'm not interested in the answer per se. I'm interested in the solution, the process of getting to it. And I want you to just show me work. So that was missing. Okay, so that was missing. All right, so having said that, that's one solution. We're going to be going over time, but let's just continue. Okay. I don't really enjoy using quadratic equations, this and that. I didn't think you would remember it, and most of you guys didn't. Some of you guys did. And those of you guys who did remember it end up not showing work. All right. came up with the right answer. I'm not interested in the right answer. It's the process of getting to it, okay, and which was missing. All right. As a result, even if you came up with the right answer, which means that you got less than some, because I want you to get used to, get into the habit of following a certain format. So this is one way of doing it. This is not the only way. Okay, the second way is actual physics, a little bit of algebra, but it's actual physics that you get to use. Okay, so the second way of doing it is the way I would normally do these problems, which is not so much algebra, but it's really good physics. All right, so that's what we will do now. All right, so let me just get out of here. Just clean this up. All right, so I need to form this one more time. All right, the second way of doing it is, I know that the motion is going to end at some point. So this thing is falling. It's got initial velocity. And then boom, it's just going to end up here. And it's going to have a final velocity. All right, so you just want to know the time it takes for it to land. Okay, there are a couple of ways of doing it. Obviously, I showed you the first one. Okay, so this one has t in it. This requires a quadratic equation, and you saw that's kind of involved. And if you're practiced enough, you can just do it immediately, just set it up and figure out your terms and come up with a one single final equation. But that stuff is involved. The second way of doing it is just use physics. All right, so I noticed that this also has t. Okay. My initial reaction was, let's use the height, pick the right formula, and then one unknown, one formula is the approach that I took. And then mathematically it got really complicated. So instead, I'm just going to do it my way, which means that I'm just going to use the second equation that has t in it, and then try to reason with this one. Okay, so that I don't have to memorize formulas necessarily. So I'm just going to write this down. Here's your initial velocity. And so this is the one that we're using. Okay, so I'm just going to grab t from there. Okay, and then we'll try to figure out where we could go with this. All right, so I'm going to rewrite the equation. You know, to isolate t, so get rid of the initial speed from the left-hand side. All right, so I got g times t equaling final velocity minus the initial velocity. And we can just get rid of g from both sides, and then we are done. Okay, so okay, so this is as far as we go right now. Okay, so now let's stop. He's isolated on the left-hand side. Okay, at this point, you would look at your numbers. All right, so you know what g is. You also know the initial velocity, but this you don't know. Okay, so that's an unknown. Okay, so you got two unknowns at this point. So the question is, what do we do? Well, this is something that you will really, really get used to. Okay, so which means that that's something that you will learn how to do by using back substitution. Okay, so we do have a formula that's going to help you in this case. So in this case, there's a second formula that has the final velocity. Okay, so that's the formula that I'm going to pull in. All right, so this is the formula that I will get to use. I'm plugging into here. Okay, so what I do is now I have a formula that I'm going to get to use, which is this formula. All right, so square this, square of the initial velocity, 2 times g times the height. All right, and then I need to solve this for the final velocity. The way to do it is take the square root of both sides. All right, so, and now whatever this says, you can just substitute back into that formula. This will have to be substituted in there. All right, so initial velocity squared plus 2 times g times the height, take the square root, minus the initial velocity divided by g. Okay, now the equations look the same, except the only thing I have to do is just move these two terms around. All right, so it's going to be minus this plus that. All right, so okay, now the equations are the same. All right, it worked out. Okay, so both of them are exactly the same now. All right, so there are two ways of doing it, and this is how it is done. Okay, so this was a little bit more complicated than what you were expecting, obviously, and obviously you guys struggled with that, which is fine, just for once. All right, so which means that the difficulty level of the test is going to get adjusted. Okay, so just focus on what's given to you. All right, so just focus on the prompts that I gave you. So I'm going to give you some similar to the prompts that I assigned, in essence. All right, so that's what I'm going to do this week. So I'm just going to make the proper adjustments so that you guys are doing better on the math portion of the test. And for whatever the reason, I thought because you guys are university students, you should be able to handle this, and most of you guys couldn't. So which means that unintentionally, the math portion of the test was a little bit more difficult than it needed to be, obviously. So I'll make sure that that is not going to happen again. I just want to make sure that you guys are doing problems similar to what's going to be on the test. So I already made that adjustment. All right, so for the upgrade portion of this test, I'm not going to give you something that's complicated. Okay, let me make a suggestion. Just do the problem related to the person jumping from the top of the bridge. Okay, for the upgrade portion of the test. So the initial velocity is going to be simple. All right, I just want to keep it simple enough so that you're getting 7 or better for an upgrade. So just upgrade this test and we'll just take it from there. All right, so those of you guys who are taking university physics, okay, those of you guys who are taking college physics, the algebra trig-based physics, you can leave right now. If you want to come back, just come back in the next 10, 15 minutes for my office hour. Okay, so this is right now my office hour. So I'm just going to continue with the math portion of the test so let's open up the test. So what do we have? This is a 4-second drop. And because of the fact that they have energy absorbing materials inside the barrel, the estimated impact time was about 0.2 seconds. All right, so determine their acceleration and comment if this acceleration is survivable. Okay, once again, the problem is worded in such a way that unless you have a really good understanding of what's going on, it's very easy to get confused. So this is not, I wouldn't wait till the last minute to start with these kind of things because you're understanding written portions of the task test your understanding of it, whether it's conceptual or problem, right? Understanding is not something that you can cram. You have to practice these kind of things. You have to go through the practice problems and then think about it, not in terms of math, but in terms of what's going on. The only thing you know is it's a 4-second drop, and then the impact time lasts only 0.2 seconds. All right, so determine the acceleration. All right, so the first thing I'm going to do is I'm going to list everything. All right, so visualize and list. So boom, they're dropping, they will hit the water. And there's going to be a final speed, final free fall speed. All right, so there's an initial free fall speed. All the way down to the water, it's going to be free fall. All right, so this is a 4-second drop. So what do we have? I'm just going to list everything. It's a 4-second drop. And motion is happening under the influence of gravity. So I'm using roughly about 10 meters per second squared for that. And what's happening is they hit the water. This becomes the initial impact speed. There's an estimated impact time, which is going to be 0.2 seconds. And they come to a stop at that point. So the question is, what is the acceleration during impact? I want to know what this acceleration is, especially in terms of G's, if the estimated impact time was 0.2 seconds. Okay, so I already have that information here. So I'm just gonna get rid of that. I want to know what the acceleration is during impact. Also know that the initial speed, free fall speed is going to 0. All right, so everything is listed. I got my symbols. I have a question mark next to what I'm looking for. I also want the answer in terms of G's because this solution is going to require an interpretation. So step number 1 is done. Okay, now let's move on to step number 2, algebra. How do you do the algebra? Well, the easiest way to do it is just go after what's given. All right, what's being asked for. Acceleration during impact means that the acceleration is going to be changing in impact. So, which means that you end up getting jerking motion. If that's the case, I have to use average acceleration formula. Okay. And this is the estimated impact time, so that's going to give me the acceleration. I know that the final speed is going to be 0. So this term is going to drop out. All right, so now this is reduced to this. Okay. I don't know what the final speed is. I don't know what the initial speed is here. Okay, so this initial speed that you have is a byproduct of free fall. All right, so which means that I need to come up with an expression for this speed. I know that speed is here. I know that that speed is this. Okay, so which means that I have to use a free fall formula for that. purpose. All right, so these are my free fall equations. Okay, now I have to pick and choose which one to use for that. All right, so I'll focus on the formulas because these are the formulas available to me. I'll take a look. All right, so final speed is what I'm interested in. So this got final speed. So this one. Can I use this one? Yeah, I can use that one, but I don't know what this distance is. It's not given to me. So forget that. And can I use this one? Depends. Do I know the time? Of course I know the time. So this is given. So that's the only unknown. So use this one. Okay, so that's the formula that I'm going to end up using. All right, so for this, that's the one that I need to isolate. Final speed equals initial speed plus g times t. I know that the initial speed here is 0, so that thing is going to be 0. So this is going to drop out. So just get rid of this. And here's what we got. It's going to be g times t. Okay, so what do? I'm trying to come up with one single formula. So do a back substitution. All right, so when you do a back substitution, you end up getting negative g times t divided by yes. Okay. So now the numbers. So g is going to be roughly about 10. This is a 4-second drop. And your impact time is 0.2 of a second. What's that? So what do you have? 4 times 10 is going to be 40 divided by 0.2 is going to be 20. This is going to be 40. 40.2 is going to be 200. All right. It's going to give you negative 200 meters per second squared. And if I say show work, do the conversion to G's and show work, then obviously you have to show work. I don't think I asked that, but let's just show work anyway. So go from meters per second squared to G. All right, so 1G is 10 meters per second squared. All right, so this is going to give you 20 Gs. Okay, so is that survivable? Yeah, I mean, they're surviving 20 Gs for a fraction of a second. You can survive up to 148 for a fraction of a second. And also, you know, John Staff survived something like this for 1.4 seconds, so it's survivable. And they did survive without any injuries. Okay, so quite a few people got this right and still failed the test. Okay, so how's that possible? The reason why you failed the test because it's a formatting test, guys. It's not that complicated. It's a formatting test. Okay, the stuff that I want to see is number one, you got enough time to list everything. Draw things out, just get used to it. I wasn't really focusing on this so much as, hey, did you list everything? And then it's free fall. Use these formulas, not the formulas on the X direction. Some of you guys think that some of you guys actually computed acceleration in free fall. You shouldn't be doing that. Acceleration is constant. It's already fixed. All right, it's already there. Just use what's given. And then the rest of the work, you guys are taking engineering physics. Don't use numbers. I didn't use numbers until I came up with a one single equation. All right. I end up reasoning. I said, oh, this is impact. So what's happening in impact? The acceleration is changing impact. So I'm using the average acceleration formula for that. I know the final speed is 0. I know that the initial speed is going to be the final speed in free fall. I pick and choose based on everything, and I keep doing back substitutions. All right, so get used to doing it this way. All right, so your problem for this week's test is that long jump. Okay, find problems similar to that. Stay away from the numbers. Stay away from the numbers. Make sure that you know how to use those 6 equations properly. Back substitution, back substitution, back substitution. Understand sines, cosines, tangents, and just reconstruct that. Just practice this until you're comfortable with it. All right, so that's what you need to do. All right, work on that problem and then find problems similar to those. All right, guys, so this is, okay, so each and every one of them is a test question. Okay, so you drop a ball and you throw a ball in the downward direction, right? Which one is gonna have a larger acceleration? The answer to that question is neither. Okay. Once the ball leaves your hand, gravity takes over. So gravity is gonna make things go faster at a rate of 10 meters per second each and every single second. So this thing is going to go from 0 to 10 with the next second and 10 to 20 with the next second. That's it. Okay. The other ball is thrown down. So the one which is thrown in the downward direction is going to have an initial speed. All right. So gravity will make it go faster at a rate of 10 meters per second in the next second. So whatever this initial speed is, it's going to be 10 meters per second faster. The explanation that I'm looking for is a correct statement. Which one accelerates more rapidly? Neither. Both of them will have the same acceleration. So gravity is going to have the same effect on all falling objects. Once the object leaves your hand, at that point, the motion is under the influence of gravity. So everything is going to speed up at the same rate. The only difference between this and that is the initial speed. It's got no initial speed. It's got the initial speed. That's it. Something along those lines is what I'm looking for. Yeah, go ahead.
So we have to mention the initial speed, even though it has nothing to do with like the acceleration it's falling. Because
Yeah,
I said the balls will fall at the same acceleration of gravity, 10 meters per second squared, because all objects fall at the same rate. It's called free fall acceleration.
Yeah, you have to kind of relate it to the question, and then you have to explain and justify. So given the fact that this one is moving faster, how is it that they're accelerating at the same rate? That's what's missing. One of the, okay, can I ask how many points you got for that? Or is this, you don't need to mention it. Okay, so that's fair. Okay, so because I was thinking it's either 2.5 or 3 at this point. Okay, so let me tell you guys something about the grade. You put down something, half a point, right or wrong, I don't care, it's half a point. You say both of them accelerate at the same rate, fair, 1 point. So there's an answer. You can say everything is going to accelerate under the influence of gravity at the same rate. That would be 2 points. Everything is going to accelerate under the influence of gravity, regardless of initial speeds. That would be about 3 points, 3.5 points. Okay, so you got most of it right. What I want you to do is I'm giving you 2 scenarios. I want you to compare. I need you to address and acknowledge that this motion and that motion are not the same. Visually, you will think that this is going to accelerate more rapidly. It's not. I want you to make that point. And also, whenever you guys are answering questions, just answer it from the perspective of talking to someone who does not know anything about the subject matter, which means that you have to explain and clarify. Okay, and a lot of you guys are answering it as if, hey, this is a knowledge test and Kenna knows the answer, so let's connect with them. Nope, that's not how it is done. You have to answer it from a perspective that a person who's doing the grading does not know anything about the subject matter. All right, so you have to kind of provide a background. When you say free fall, what do you mean by free fall? Just write one single sentence. We're under the influence of gravity. When things are moving under the influence of gravity, they will accelerate at a constant rate. They will speed up at a constant rate. All right, so whatever the initial speed is, they will be moving 10 meters per second faster during the next second. Okay, that would be a full explanation. Okay, notice that when I do that, I don't leave anything to any sort of assumptions. I don't assume any knowledge on the part of the grader. Okay, so that's what I'm looking for. This is the way you guys should approach it. These are not necessarily knowledge tests. Knowledge test is the multiple choice. A little bit of conceptual thinking, but mostly knowledge test. But the conceptual portion of the test, I know you know the answer, it's there, but the explanation is missing. Okay, so
to correct my answer, I would just add that even though one's thrown faster initially, they're still going to fall at the same rate, because I'm just
yeah, what's missing is not, you're not correcting anything. You're just, justification is missing. It's not incorrect. Everything you said is correct. You just need a little bit more in terms of a justification. All right, so that's number one. Okay, so let's move forward because I need to cover something else because I want to make this part of the recording. Evidently, the recording that I put out was missing one of the questions. I'm not, okay, so this is covered. The next one. This is case number one. Case number two. All right, so one ball thrown in the upward direction, the other one is thrown in the downward direction. Okay, so which one is going to land first? This is not the question. This is what happens. A lot of people, some of the people actually misread the question, I think. Okay, so this is thrown in the upward direction. The second one is thrown in the downward direction. All right, which one is going to have a larger final speed? Which one is going to have a larger impact speed? Okay, so once the ball leaves your hand, the motion is under the influence of gravity, so that becomes free fall. That's the meaning of it. In free fall, everything is going to accelerate at a constant rate. Okay, but that's not the answer I'm looking for. That's knowledge. Okay, there is a huge difference between knowing that and being able to justify what's going on here. So this requires a careful explanation. All right, so let's follow this for 1 second. Second later, it's going to be moving at 30 meters per second because it's accelerating under the influence of gravity. I will place the ground right here. And then I'm going to follow this one. Okay, so going up against gravity, it's going to slow down at this rate. So next second is going to be 10 meters per second. The following second is going to be 0. And then within the following second, it's going to go from 0 to 10. Within the next second, it's going to go from 10 to 20, right? All right, so notice that at identical points, they have identical speeds. So if you let it drop 1 more second, it's going to be 30 meters per second. Okay, so how do you explain this? Well, I explain visually. All right, so under the influence of gravity, going up against gravity, you will slow down at a constant rate, and then you will speed up at a constant rate. When you get back to the initial location, downward speed is going to be exactly the same as the upward speed at that point. And within the next second, it's going to be moving 10 meters per second faster, so just like the other one. So both of them will have the same speed. So it depends on how you want to explain it. I'll leave it up to you. I just look at the quality of the explanation. A lot of the people said acceleration is constant, therefore they will hit the ground at the same speed. Those people actually came up with an explanation. That kind of explanation lacks justification. You will get 2.5 to 3 points for something like that. Complete explanation requires that you kind of follow the motion of this. This is going to slow down. It's going to speed up back to the original speed. And then which means that both of them will have identical speeds at some point in the downward direction, which means that they will have the same final speed. So this requires a little bit of finessing. explanation. The other one that most people end up missing is this one, the ball stops or something, right? Either the explanation was completely wrong or it was incomplete. A lot of the times, if you're getting 2, 2.5, 3 points, it's not that the explanation is wrong. It's just that it needs more justification. At the moment the ball stops, is the acceleration 0? No, what's 0 is the speed is 0. Okay, the acceleration is how fast something is slowing down, how fast something is speeding up. That's what the acceleration is, or how fast something changes direction. At this point, it's not moving, it doesn't have a direction either. So the question is it moving before it stopped or after it stopped? If the answer is yes, it's always accelerating. That's it. I'm looking for a simple explanation. So one of the speeds is 0, one of the velocities is 0. If the other one is not, it's always accelerating. Okay, it's not like a bus stop. It doesn't come to a stop and stay there. It's part of motion. It's part of motion. All right, so the explanation that I'm looking for, in essence, is A, it's moving before it stops, it's moving after it stops, it's always accelerating. And you can figure out what that acceleration is. 1 second before, it's moving about 10 meters per second. So it goes from 10 to 0 within a single second. The acceleration is 10. Within the next second, it goes from 0 to 10. The acceleration is still 10, same as gravity. Okay, so I'm looking for something along those lines. I'm over justifying it. You don't need to over justify it. The only thing you need to know is if it's moving before and after it stops, it's always accelerating.
Okay,
So
that was actually my answer. I said the ball's accelerating at the moment it stops because it is moving before and after it stops, and I still only got 3 points.
All right, just hold on to that one. Just wait for me. Okay, so what's missing there is what the acceleration is, right? Okay, so just remember what I just said. Don't assume any knowledge on the part of the person that you're explaining it to. All right, imagine that you're talking to someone who thinks that the acceleration is just slowing down, and that's what most people think, or speeding up. Most people think that the acceleration is speeding up. The car got into an accident while the car was accelerating, which means that people go, oh, so that's a speeding car. That's what they say. That's not what it is in physics, is it? All right, so what's missing there is justification is there, but the explanation is missing. The explanation is you assume that I knew what acceleration was. You're assuming something on my part. Don't make those assumptions. All right, just assume that you're describing something to someone who has no understanding of it. So give the answer, explain it, explain what acceleration is. Acceleration, I already gave you an explanation for it. I said it's speeding up, slowing down, and changing direction. I said the changing direction is not applicable. A lot of you guys put emphasis there because this thing is not moving at this point. There's no direction involved. All right. In this case, the acceleration is literally speeding up and slowing down. That's what it means. All right. So if it's moving before it stops, it's accelerating. If it's moving after it stops, it's accelerating. Notice that not only did I provide what acceleration is, a definition of acceleration is, also I justified. All right. Okay. So this is actually, I like the fact that you're asking these questions because that's part of the frustration. Because you're assuming knowledge on the part of the grader. Just don't do that. Just assume that you're talking to someone who knows next to nothing about it. Because you guys are assuming that this is a knowledge test. Nope, knowledge is assumed, okay? Because it's been already tested. I know you know this stuff. Are you able to explain it? Are you able to justify it? So that's what I'm looking for.
Is there any point deduction for over-explaining something?
There's absolutely no point deduction for over-explaining. So some of the people type real fast, no. But stay away from poetry, okay? When I say poetry, I don't mean rhyming things. People, if you watch the video, people come up with answers which are not related to anything whatsoever, or it's a side topic. Don't explaining is fine if you can over explain it. If it's still relevant, it's not going to hurt you, obviously. But don't put stuff which is not really related to anything that we're discussing. Just focus on the physics. This is related to acceleration. Definition of acceleration, which is speeding up, slowing down, changing direction. In this case, it's slowing down. In this case, it's speeding up. It's moving before it stops, moving after it stops, if it's in with the definition of acceleration, and that's it. Over explaining it, absolutely, I can over explain it, which I did because that's what I do. I get paid for it. It's moving at 10 meters per second before it stops. It's moving at 10 meters per second after it stops. The acceleration is 10. I over explained it. You don't need to. Okay, just cover the essentials, and then if you got time, boom. Anyway, another thing that I need to mention is 5 minutes. Is all you got. It doesn't give you any time to research. And notice that it comes right out of the lecture. All right, just make sure that know how to explain these observations and explanations properly. All right, just you need to practice before the test. And obviously during the test, it's not a good time to research. You can Google this stuff. It gives you knowledge and information, which I'm not interested in. I'm interested in understanding, obviously, that allows you to be able to explain and justify. All right, so that's it. Okay, let's move forward. Okay, so I did explain and justify 3 of the main observations for this one. Okay, what else do you guys have?
That was actually all I needed. It was very helpful. I think I'm gonna go now because I kind of have another class work to work on.
Okay,
thank you so much.
Okay, hold on. Okay, okay, I need to give you some participation points for this one. Can you do me a favor? Can you give yourself 50 participation points and hold on to these participation points until the end of the semester? Because I realize I'm giving you 50 participation points. Just hold on to these participation points until the end of the semester because I will need these back. This is going to become part of your participation grade. when you guys show up with questions like that. I just want to reward you for it, because this exchange was important, because I was able to understand where you're coming from and what the source of the frustration is, because some students know the answer, but they're not able to explain it because they need this sort of feedback. So this was awesome. Okay, so okay, keep coming back every single week if you have these kind of questions. All right.
Okay,
so
I will.
Okay, I enjoy this. All right, who else? Can you explain? Okay, so
I'm just wondering about something. So I noticed how you said on the recitation how like the math multiple choice, how like, yes, I agree. Some of the questions in there were they were definitely hard to understand because it felt as though it's like I didn't like remember us learning about these sort of things. So when it comes to the upgrade test, like are the questions going to be upgraded or is it going to be the same?
Okay, so here's what I'm going to do for the upgrade test. Okay, for the upgrade test, they're not going to be, if it's multiple choice, let me just take a look at the quality. Are you taking, hold on, which physics are you taking? Are you taking?
I'm taking essentials of physics.
Essentials, so you're taking the calc-based physics. Okay, so multiple choice, I'm going to keep it in multiple choice section. All right, and let me just go over the questions, because what I did, I blocked out certain questions in my mind, and then I randomized the race, I randomized the rest. Anyway, so, and evidently, when I thought I was blocking out certain questions, evidently, I did not block them out correctly, and next thing you know, you guys end up getting the entire test bank unintentionally. All right. So let me just go over the questions. Just want to make sure that it's related to what we do in terms of problem solving, and that's going to become the upgrade test. Okay, that's what I want to do. So, which means that let me just go over that. Okay, in the future test, now that I know how to block questions, we're not going to have the same problem. So the questions will be related to what we do during the lecture. So that's not going to happen in the future.
Okay.
So that I think that addresses your question.
Yeah, it does.
Okay, and another thing that I need to mention is, because so many tests, guys, failing one test makes no difference. Your lowest test rate is going to get replaced by your participation grade, this and that. So take care of those participation quizzes as well. There's you're entitled to facial credit percentage points with each passing test. You guys will get better at it. The worst case scenario, you take the final test, and then by then you'll have a really good idea of how to do this sort of stuff. And the only thing that really matters is your final test grade. Okay, literally on the final test, you will have the same multiple choice questions, you will have the same conceptual questions. A lot of the problems will be similar. So, which means that by the time you take the final test, if your exit competency is an A level, you will get an A in this course. Most people usually get Bs. You will struggle initially, eventually you will catch on. All right, so don't get discouraged. Okay, it's a learning experience. You'll get better at it, and in the long run, even if you don't do physics, the sort of thinking that involves the sort of thinking which is involved in physics is exactly the same sort of thinking that's involved in every single science. So it'll make you better. It'll make you better in whatever it is that you guys are doing in the future. All right, so Zionat's question is the one that I'm going to focus on, because I'm looking at the chat right here. She says, can you explain the Diana question? The acceleration was survivor. Why did she die? Okay, so that's a really good one. Okay, so why did she die? Okay, so let me just go over some of the answers just to give you an idea. Well, she died. Okay, let me figure out how best to do it. Let me just approach it from a common sense perspective, because that's what I get from students usually. Most students who get it, I don't want to say wrong, but most students who actually fail at this come up with an explanation like the following. She wasn't wearing a seatbelt. She went in the opposite direction of the acceleration of the car. She hit something hard, not energy absorbing, blah, blah, blah. Okay, so what's wrong with those answers? Nothing is wrong with those answers, except they're not really related to anything that we discussed directly. All right. Let's focus on the reason why she died. She wasn't wearing a seatbelt. All right, so which means that her impact time wasn't the same as the car's. All right, car got its impact time from the crumple zone, okay, which is about 1/10 of a second. At reasonable speeds, it's about 20 Gs. If you're not wearing a seatbelt, your acceleration time is much shorter. All right, because she wasn't wearing a seatbelt, her acceleration time was much shorter than the car, so her acceleration was much larger than the car. Okay, now let's focus on the acceleration. Acceleration is what kills you, what maims you, what breaks your bones. Acceleration is not only how fast you speed up, slow down, and change direction, but it's also related to the impact time. It's inversely related to the impact time, right? Shorter the impact time is, the bigger the acceleration is. And without the seatbelt, her impact time was much shorter than the car's impact time. As a result, she died. She didn't survive. Okay, so this is a long explanation, but notice that I explained and justified everything. All right, so the short answer of what I just said, I would have said on the test, this requires a little bit of an advanced thinking, because you got 5 minutes, and you know it's a main observation, right? And you know that's a question that's going to come up, because it's a big concern. They say you have to wear a seatbelt, and why do we have to wear a seatbelt? Does that violate our constitutional rights? Blah blah blah. People come up with all sorts of BS, not to do the right thing. All right, so what's the purpose of it? The purpose of it is, obviously, acceleration is what kills, what maims, what breaks your bones. Acceleration is inversely related to the time of impact, right? The shorter the time of impact is, the larger the acceleration is. All right, so the car gets its impact time from the crumbling zone, which is about 1/10 of a second. At reasonable speeds, it should be about 20 Gs. Without the seatbelt, your impact time is much shorter, your acceleration is much larger. And that's the reason why she died. All right, now notice that I explained and justified everything on that one. All right, Zion also has a second question, which also, okay, Zion, I'm gonna give you 10 points for that question, so hold on to it because participation, these questions will be the participation points I'm giving you will become part of your actual credit. All right, so just hold on to it. I will need those participation points at the end. So second question is, what's the difference between 1/2 AT squared and 1/2 GT squared? All right, you're on the right frame. Okay, so each and every single formula is a summary statement of physics. I can go blah, blah, blah for 2 hours. At the end, this is your summary statement. Motion is predictable when the acceleration is fixed. This is a generalized formula. And I'm dealing with motion along the x direction. This is strictly for motion along the x direction, this axis. Okay. Horizontal motion, you fix the acceleration, you know the time, you know the location, and you know the speed at this time as well as at this location. That's it, it's predictable motion. Okay, so that's the meaning of this motion. All right, so this is a specialized case. This is free fall. This represents motion on the y direction and under constant acceleration. This is roughly about 10. All right, so how you pick a formula tells me how well you understand the concept. You cannot just pick formulas. You cannot use these formulas for this kind of motion because here X means something. X means motion along this direction, and traditionally the free fall takes place along this direction. So you can only use these formulas for that. All right, so some people end up starting out with this formula, all right, for whatever the problem was. Immediately you end up losing points there. All right. In the future, within a few weeks, in reality, when you pick a formula, you will have to justify why you're picking that formula. You will have to, every time you introduce a new formula into your solution, you have to explain why you're picking that formula. Okay, so which means that you have to have a really good understanding of what's going on. We don't pick formulas by just looking at the symbols. We pick formulas because formulas represent certain things. You can use these formulas only if the acceleration is constant, and obviously this deals with horizontal motion. And you pick these formulas because you're dealing with free fall, all right? So despite the fact that mathematically the manipulations are the same, this formula is not the same as this formula because the motion here is along the y direction, this is along the x direction. All right, so that's it. So you're gonna give yourself 5 points for that one as well. All right, so what else do we have? Let me just open up the chat. Okay, guys, if you have any other questions, just put it in the chat or just talk. Okay, so those were the questions. What else do you guys have? Okay, so that covers everything else. All right, because you guys are here and I didn't have a lot of time for it, let's just focus on circular motion, just briefly. Okay, in terms of circular motion, I'm gonna edit this and make it part of the video. I don't have a lot of questions to ask. I'm not gonna ask any math questions, but there's 1 or 2 conceptual questions that I wanna cover. In circular motion, you know the speed is not changing if it's uniform circular motion, but the direction of the speed is gonna change. Okay, so here's the trajectory of this motion. So this thing is gonna be moving at a constant speed. So the speed is not gonna be changing. And you know this thing is accelerated because the direction of motion is changing. Okay, so that's an explanation, but the justification is missing. So how is it that this is acceleration? Given the fact that the direction is changing, guys, that's an explanation. That's a textbook explanation. That's a definition. So that lacks justification. You can justify that the acceleration is directed towards the center of a circle because if you're driving, the unstrapped objects will still move in the opposite direction of the acceleration, right? So if you're inside the car, you will experience a push in the opposite direction. As a result, you know that the acceleration is going to be directed towards the center. So that's what you need to come up with. So that acceleration is going to depend on your speed, and it's going to depend on the radius of the circular motion. Okay, now out of that, tighter the turn is, larger the acceleration is going to be. So that's one conclusion. The tighter the turn is, the larger the acceleration is. The second one that you can come up with, obviously, the faster you go, larger the acceleration is going to be. Okay, so if there are multiple choice test questions, it's going to be related to that. All right, so for a given speed, the tighter the turn is, the larger the acceleration is. And for a given radius, the faster you go, the larger the acceleration is going to be.